Welcome to my talk on the SoC support in the kernel. My name is Arnd Bergmann. I'm maintainer of the SoC support, specifically the ARM SoC support, and also I'm responsible for bringing in new architectures into the kernel. So I'm also overall the architecture maintainer. And today we talk about SoCs overall. The first thing I want to make clear is what it means for an SoC to be part of the kernel. There's like 5 distinct levels of upstream support that one can have in the kernel. There's ideally a platform would be fully upstream supported, which means everything works out of the box. You can install any distro and you expect all the drivers to work. This is the default on most server platforms and on things like PCs. In embedded systems, usually the best you can hope for is that there's a small number of patches that get shipped by a vendor. And with those patches, you can update them to the latest kernel, something works. And then we get all the way down at the bottom, the red one, that means there's a kernel running on a machine, but there's no way anybody is going to touch it anymore. There are no more updates. So what we're focusing on is the 2 green ones, which means people are using current kernels or they will be upgrading to future kernels once they have become the long-term stable releases. The process of supporting a platform upstream is what is usually called bring up. And I think that matches fine with the picture. The higher you get, the better a platform has been brought up. So bring it up all the way means it can basically run forever on any new kernel because everything is supported. And if you only do bring up half the way, you might get to 1 kernel version that you can support, but then you would never have an update on it. So if this is called bring up, then there's obviously the opposite of that, which I would call the bring down. The breakdown happens over time. At some point, people stop running the latest kernels. There might still be the stable releases that somebody has. And over time, people stop moving to the next stable release. They only get updates from a certain vendor. If they get updates at all, then there might only be bug fixes. And at some point, you might have hardware that still runs, but it's not getting any changes at all because nobody is actively building kernels anymore for this platform because nobody cares. So for the upstreaming, there's a couple of things that make it hard for you to upstream a new platform. For the most time that I've been working on this, the main obstacle was GPU drivers. If a platform doesn't have a GPU driver, you're obviously not at the highest level. You need a driver from the vendor to make it work, and that means you still have to have patches. Now, this has changed very substantially over the years, and now for, I'd say, 5 out of the 6 most popular GPUs, there are drivers in the kernel. Most of them working fine in most cases, some not working as well as the others, and there's still one that doesn't have any drivers. Then there's the Android patches. A lot of platforms ship with an Android kernel. And for a long time, there was a huge set of patches maintained by Google specific to Android. And you couldn't actually run an Android user space without those patches. And that, again, has improved a lot over the years. So now you can actually have a mainline kernel, put it on an Android device, and still run all the Android user space. But there are still patches that need to be upstreamed. And this will also continue improving over time. Then a problem that we won't be able to solve is the very short time to market, especially in high-end devices, which have a very short life. There's just no time to upstream everything before hardware hits the shelves. In some cases, patches are not upstream before the last device is sold, and then you're still upstreaming the patches after the device has been replaced by something else. And this is less of a problem for the low-end devices, which tend to have a much longer life. Then there's the short lifespan is directly related to the short time to market, of course. And then there's unannounced products. So some companies are very good at upstreaming all their platform patches before the hardware is even out or before it has been announced. There are some sneaky ways you can get in patches without saying what this product is. You just say a future product will use this new driver. You don't have to actually announce something. But in other cases, that just doesn't work because somebody, like nobody might know that you're working on a specific product line at all in the new market. And then in some cases, SoCs do something new. So there might be new subsystems that are needed. And if there's no subsystem for it, kind of can hack your way around it, write a new driver, but that won't make it into the kernel if there are lots of other companies that have the same need. And then we have to agree on one subsystem first that completely abstracts the user interface so that every SoC can have a device driver for it. What's even worse is if you have more than one subsystem abstracting the same functionality, because then we have to decide which one to use, and that can take even longer time. Now for a world map of the CPU architectures. This is what I, as a kernel developer, imagined the world to look like in 2010. This includes all the machines that were supported in Linux. It doesn't actually include a lot of other things that did not run Linux. And there you can see what the world used to look like back 10 years ago when Linaro was just being formed. So you had a bunch of equally important architectures in all kinds of different markets, from microcontrollers all the way up to the data center. Two things that you don't see on this map are 64-bit ARM and RISC-V, which were both being worked on by a couple of people, but they hadn't yet talked about it in public. So these were clearly not there yet. And in particular, the middle of this picture shows the SoCs. So the SoCs is what I'm interested in at the moment. On the top, you have the data center chips, which tend to be less interesting because they just work in a lot of cases. There's much less variety in the hardware. And then on the bottom, we have platforms that are for microcontrollers, for FPGAs and DSPs, which are all quite different platforms, but they're all are usually not the ideal place for a Linux system, for a general purpose Linux system, or even for most embedded systems. Inside of the SoC bubble, back 10 years ago, we saw ARM, Super H, PowerPC, and MIPS. And what's interesting is that ARM was basically the low end of this. So ARM were the deeply embedded ones, the 200 megahertz ARM9s. They were single core, single issue. They had very little memory, whereas everybody else was going into out of order 64-bit big SMP systems, much larger memory. And also the other thing you see is that all the really nice ones back then were big Endian. Then let's look at the generations. I've tried to categorize all the SoCs that we're dealing with into 3 distinct generations. This is a chronological view. So on the left side, you see the things that started appearing in the early 2000s, where you had all those different architectures. You had ARMv5 at some point, you had MIPS, PowerPC, Super H, and lots of other small ones. You had fairly low speed I/O, you had fairly little memory. And then at some point, we started seeing ARMv7, where everything got a little bigger. And then, of course, ARMv8 with 64-bit support and a lot of high-speed I/O and much larger memory. The low-end parts, however, they tend to stay around for a while because they're still much cheaper. But then again, they're not the same. They sometimes also evolve. So you might have a different kind of low-end platform. But they still fit nicely into these three categories, I think. And the most important distinction that I'm trying to make here is the amount of memory that you have. So in the earlier generation, you had something as little as 2 megabytes of RAM still running Linux. And it didn't really go all that much beyond 128 megabytes. And then the middle generation, you have the larger 32-bit systems for embedded. 256 megabytes was quite a lot a while ago. It's now the absolute minimum. For an ARMv7 system, you have something up to 2 gigabytes typically. And ARMv8 on a 64-bit system, you usually have a lot more memory. So that's 2 gigabytes or more. And then I list all the different interfaces here, but really a lot of the SoCs only have a small subset of those interfaces. But if they have an interface, it's probably in this speed grade. So if you have an ARMv8, you would not see a 2G modem on it. You would see a 4G LTE modem on it, or a high-speed Ethernet. You wouldn't see a 10 megabit or 100 megabit Ethernet. But let's look at the memory usage. So this is a graph that shows all the different kinds of DRAM that I could find just by taking a snapshot of the product listings on Mouser.com. And for every color corresponds to a specific generation of DRAM. And you can see that most of these graphs have something like a V-shaped curve. So on the left, you can see that with every doubling of the memory capacity, the price per gigabyte or per megabyte goes down up to a point, and then it goes up a lot again. And this means, for example, on DDR3, you can spend another 20 cents to double the capacity between 128 megabit and 2 gigabit. But after a point, it gets really expensive. So there's a kind of optimum capacity for each memory device. And you can see how that fits into the generations of SoCs. So as any SoC that might only have DDR1 memory, the optimum point is having 64 megabyte capacity based on the fact that you might only have a single 512 megabit chip. You could have two of them, then you have twice as much. But you can't really have much more than that, or it gets really expensive. And then with DDR2, you get twice as much. With DDR3, you can actually get 2 times or 4 times as much as with DDR2. So the cheapest memory that you can get at the moment is a 4 gigabit chip. In a typical system, you would see 1 or 2 of them on a small embedded system, which means you have either half a gigabyte or 1 gigabyte of RAM total in the system. And this is the ideal operating point, like the ideal marketing point for a 32-bit system at this point. It's also interesting that the 32-bit chips without DDR3, they started disappearing along with most of the other architectures. So if you don't have an ARMv7, you probably don't have DDR3, and then you're already stuck in this lower capacity category, which means it's much less useful because it's always easier to start out with more memory and then just be more wasteful to the memory and have it last longer. And then for 64-bit systems, you are immediately at the LPDDR4 column. So in a 64-bit system, having less than 2 gigabytes of RAM is also not ideal, because then the memory can become quite tight. With 64-bit, you need maybe 30% more RAM capacity for the same workload, just because the pointers are larger and then the code may be a little larger. And that gives a pretty good distinction between the 32-bit systems running DDR3 and the 64-bit systems using LPDDR4. The other thing is on 32-bit, you really don't want LPDDR4 because once you grow beyond 2 gigabytes, it gets really hard. You need high mem, the memory map gets crammed, and it becomes much less, like the advantage of doubling the memory is not really there, but it costs a lot more. So how does this correspond to the memory requirements of distros? So when you look at Debian, which is probably the most commonly used desktop distro on any of these SoCs, the current requirement says 256 megabytes. You can probably do with a little bit less, but if you go below 256 megabytes, it can become painful really quickly. And you have distros like OpenWRT, which now say the absolute minimum is 64 megabytes, but really you should have 128. And this is distro that's highly optimized for memory usage. You can see that this has grown from like 16 megabytes 10 years ago to 128 megabytes right now. Alpine Linux is also a desktop distro that's even more optimized for memory usage than Debian, and they list 100 megabytes as the absolute minimum. An interesting one is the Sonos smart speakers, which were in the news earlier this year because they have deprecated the usage of some of the older machine types. And I had to look it up what they are. So those came out around 2008, 2010, and they were already using old technology back then. And the smallest ones have 8 megabytes of memory installed. And those were still supported up to now with running Linux 2.4, and now they still say they will get bug fixes, but they do not get any new features. So they are in a really tight spot there. And the smallest that I could find is the Microsoft Azure Sphere, which so far is running on one type of SoC that has 4 megabytes of integrated SRAM. So that's the smallest that people are still working on and supporting as of today that I'm aware of. So let's look back at these generations and where these generations are now. The oldest one would be the low-end category. Now these still exist. And when you look at what's out there, these are really the absolute cheapest ones. What's particularly interesting there is that these run all kinds of CPU architectures, whereas the higher end ones, they've all moved to ARM. The low end ones run on all kinds of architectures, including new chips. And these are the ones that I listed, they're all supported by Linux today, or they have patches that have been posted recently. These chips usually cost under $5. You sometimes can get a whole board under $5 running Linux based on any of these chips. But it's really the race to the bottom. You have the absolute minimum that you can use, and every cent counts. So when you get to the point where adding another 20 cents to double the memory capacity breaks your budget, then this is where you're at. And these are usually the same kind of operating point where we used to see ARM9 dominate the world, while the higher end ones were running on other architectures, and it's completely reversed now. And then we have what we currently see as most of the deployments still. The 32-bit ARM v7. We used to have a lot of different systems initially. starting like on the low end, but then starting with the Cortex A8 and then all the other chips up to the A17. What I find most interesting there is that it's consolidating on this one design point where most of the systems that are still being shipped and the new SoCs coming out, they use something like 2 or 4 Cortex A7s. They almost all use half a gigabyte or 1 gigabyte of DDR3 and kind of all end up in the same operating point. There used to be higher speed cores and higher speed interfaces, but those are slowly getting away as people move to 64-bit. And the lower end usually doesn't make sense once you get something for the same amount of money that's significantly better. So if you used to have a Cortex A8 based chip, you can now get a Cortex A7 with 4 cores for the same amount of money. So who's going to buy the Cortex A8 one? And then some of the other exceptions are interesting. So the only chip that is still successful that I could find that's not ARM is the MediaTek MT7621A. That's the MIPS chip that also has DDR3. It's one of the few ones that do. And that's still being put in a lot of Wi-Fi routers. And then the third category, 64-bit, obviously is taking over everything in the long run. But it's not quite there. And it's competing with x86 at the moment. So a lot of the embedded systems have an x86 SoC or regular x86 CPU. Sometimes you get into the same price point with a higher end ARM SoC, but actually most of the market is really x86. So when you're looking at the supported machine types that we see in the kernel, there are on 32-bit ARM, that's really the large majority of all of those. We have way more 32-bit ARM machines than everything else combined. But then again, most of these are also older machines that are probably on their way out in the long run, that have stopped getting updates in field. People might still be using them. They might be running their own code, but the products are on the way of the bring down. When we look at how this changed over time, here we should look at the yellow and green lines. You can see the yellow line is starting to stagnate. So 32-bit ARM, we're still growing, and we're at a much higher level, but the growth is getting smaller. Whereas in 64-bit, there's still the exponential growth that you expect to see from a new platform. And I expect this to go on for another like 5 to 10 years, at which point we'll be removing more 32-bit architectures than adding. So let's look back at the world map and how it's changed. One of the things that happened a few years ago, in 2018, I removed 8 or 9 architectures from the kernel. And these have all been on the bring down path. You can still buy some of these, but none of them have seen kernel updates in a long time. So nobody is working on upstreaming of any new patches because nobody's interested in these. They would run some old 2.6 kernel and not get any updates. And at that point, we just removed them all. Also, a lot of those cores, they still live on in microcontrollers because they are fairly power efficient, and the companies that made them still own them. They might have already had microcontrollers, you just don't run Linux on them anymore. So all of these are consolidating to ARM. Actually, none of those went anywhere else. Then another thing that happened is that a lot of CPU architectures just completely end at some point. These are still all sold. People are still working on them. But after having released new CPUs every 1 or 2 years, all of these stopped getting updates, and these are all the latest generation of a CPU core by one of these companies. And after 2017, they have not released a new one. It may be that I got one or two of these wrong, but most of them I don't expect to see any updated CPU cores. But people are still putting those into products. Then we have seen a lot of migration of users away from the architectures that are kind of obsolete, and also of the architectures that still have a big market share and are not obsolete yet. And these are all moving to either x86 or ARM, so those boxes are getting bigger on our world map. And then we have architectures with new hardware, and that obviously includes x86 and ARM. But there were a few surprising ones. So for RISC-V, I checked, there were actually something like 50 new microarchitectures done in the last year, but not a single product based on that. IBM still has 2 server architectures that are not SoCs, but they still make a lot of money out of those. And then some of the other architectures, people are either shrinking the existing designs or they are making new cores and hope to still have a business beside ARM and RISC-V on the embedded space in the future. One very interesting point that I found is that almost all the big Endian ones are getting away. So we have a couple of architectures that have gone away from big Endian products, from new big Endian products, and just changed the designs to little Endian, or changed the software if you can run both of them. We had some companies that used to have big Endian MIPS and then moved to little Endian ARM. We had those that are just not producing any new chips. And we had those that moved to RISC-V instead of moving to ARM. And the only one that really remains is the IBM Z architecture. So with that move, the world looks like this, and IBM is getting pretty alone in the upper right corner. But we also had new architectures. Most importantly, of course, RISC-V, as I said, there's very little in terms of architectures that we already, like SoC architectures we already support in the kernel, but everybody thinks they will be big in the future. And Synopsys Arc is similar in a lot of ways, but very different in other ways. So Synopsys Arc, the Arc has been around for 25 years, almost as long as ARM, maybe even, I don't know, it's been around for a long time. They have a fairly active ecosystem. They have had a number of SoCs running Linux, but my impression is they also get more into the space that doesn't run Linux. But it's very hard to know because they don't seem to be as aggressive about upstreaming the platform support. So either there are no platforms, or there are a lot of platforms that they don't actually upstream. And then there's a couple more architectures. Basically, most of these have already been obsoleted by RISC-V. So some companies apparently decided on the move to RISC-V and then decided to upstream their existing platforms because they recognize that having open source support is nice. And then you have some DSPs that we merged a couple of years ago. But these seem to never have caught on a big market running Linux. So they're also running other things, but these are still around. So the new architectures, I put them there. As I said, Arc is huge. They are probably the second most shipped architecture after ARM, but they're not very visible in Linux. And RISC-V I put there because there's a lot of work going on, even if you can't really buy much hardware. Just to prove my point here, I made a list of all the architectures and how the number of change sets in the kernel changes over time. And you can see that 32-bit ARM is already shrinking to half of what it used to be. 64-bit ARM keeps growing, and currently they are roughly the same. So 32-bit ARM, 64-bit ARM, and 64-bit x86, they're about the same, and they make up most of the changes overall. PowerPC had a pretty good run, but they also seem to be declining. And then you have MIPS and S390 as something that you can still see, but they're way at the bottom, and everything else is really in the noise. This is the noise, as you can see. RISC-V now sticks out a little bit at the end, and then you had others like Spark and Arc that had times of activity, but are not really there anymore. So this is where we're at the moment. I get to my predictions for where we will be in the next 10 years. I think that the three architectures, x86, ARM64, and RISC-V, will basically be splitting the SoC market three ways. Very hard to tell which one will be bigger, because we hope that it's ARM. Upstreaming will get better. We will still see 32-bit chips get released for a long time, but I think that in 2030, we will have seen the last one getting released. And then probably another 10 years after the last release, while people put that chip into new products, and another 10 years of continued usage of these products. So there's probably another 25 years maybe that people will use 32-bit chips, which is very important to me because I just spent a long time on the 2038 problem. And I don't think there will be any new ISAs. I think that time has gone, but 128-bit computing, either making pointers longer, making physical address space longer, or we got the talk on Morello, and with the Cherry architecture, there was a talk last week that also has a pretty good chance of at least starting to become visible over the next 10 years in products. And I don't think that any of the other ones will still make it. Okay, that's it for my talk. And now I shall have a look at some of the questions. I saw you guys typing away there. So Drew is asking, did you discover ARMv7 systems using more than 2 GB in your research? Yes, I did. There are, most importantly, the TI Keystone 2 systems. There are some that use up to 8 GB, and they will still be around for a couple of years. There's an interesting discussion going on about removing high-mem support, which would limit the maximum usable size to something like 2 GB for any 32-bit architecture. And if we do some tricks in the kernel, we may extend that to 4 GB. But 8 GB systems, we basically have to wait until they are all in the bring down phase and don't get updates to later kernels anymore before we can actually remove the high-mem support. And then John asks, are people migrating to ARM and running Big Endian, or actually switching to ARM and Little Endian at the same time? I'd say both happens, but the latter is more common. There are some large code bases where people rely on old code that is not Little Endian safe, and some of those run it on ARM using Big Endian kernels, but it is getting less and less common. And then there's a question in regards to smaller embedded systems. What are the minimum requirements for running Linux besides size of memory? On the philosophical side, could there be Linux without support for MMU? Yes, there's actually a lot of that. I had on one of my earlier slides, I showed there's actually ARMv7M would be an example without an MMU. And we have lots of other systems without MMU, and those tend to be the smallest ones in particular, because there is still a demand for very cheap systems with not a lot of CPU performance, not a lot of memory, And if you have an ARM CPU, that means you probably have a Cortex-M, and they don't have an MMU, but they do run Linux. And that's it from me. Any other questions? Yes, question from Ralph. Can you provide some general info about the SoC tree? What are the criterion for getting code included? Is there a website mailing list? Yes. So this is a topic for a whole new talk, of course. We have the soc@kernel.org address where we take patches that are SoC specific. Usually we take patches from maintainers that are already maintaining an SoC family. But if you have a new SoC and you want to maintain it, or there's already support and in the kernel, but no maintainer left, then soc@kernel.org would be the point of contact. You just write to us if you have something about upstreaming. Generally, we tend to be fairly liberal about adding new SoC support, even if it's very rudimentary. But then if a very rudimentary port stays around for a couple of years, we'd also throw it out very quickly, because it's clear that once the bring up has stopped, it can only go down from there. And if it's not functional, then we can throw it out. Robin asks, in your role as SoC sub-maintainer, are there any specific safety, security, hygiene aspects you care about? I don't think anything specific. We tend to work the same as all the other maintainers. I want to know who I get the patches from. I want signed Git tags when I get patches. Most of the work we fan out to the next level down. So we basically only take patches from the platform maintainers, and we have to trust them to do the right thing. So the main thing we do is we limit the number of people we pull from regularly. And there's a question, is there a specific ARMv7M SoC board that you can recommend for particular ease of getting started? ARMv7M, I generally do not recommend doing any of it. The best supported probably is still the STM32F7. That is the one that I remember last seeing patches for. If you're interested more in NoMMU than ARMv7M, there's the latest one that was added is the 64-bit RISC-V board. That's actually the only RISC-V board that's supported in the kernel. That might be interesting just for fun reasons. I would not recommend any of that for a product. But generally, having like there's the Atmel SAM9X60, which does have an MMU, but is in the same space. So that's the ARM9 CPU that was recently added to the kernel, and that is very well supported and would be in the similar price range as any of the Cortex-M systems.